In this lecture, we talk about unique factorization domains being integrally closed. So first, recall the definition of being integrally closed. So say A is an integral domain and it has a field of fractions, say K. So then A is called integrally closed or normal if the elements of K that are integral over A are in A itself. So more succinctly, so say you take an element alpha in K, which is field of fractions of A, then alpha is integral over A. This would imply alpha is in A for integrally closed or normal A. So now we come to the big theorem of this lecture. So this theorem is, so let A be a unique factorization domain, then it is integrally closed. So what we need to show is this: you pick an element A in the field of fractions K of A, and we have to show that this A is integral over A if and only if A lies within A. So first direction, in this direction it's very easy, and this we have seen before. If A lies in A, then A satisfies a monic polynomial like this: x minus A equals to 0. So therefore A is integral over A. So if you pick up any element A in A, then it is obviously integral over A by this equation. Now the opposite direction is what is requires the proof. So conversely, you pick up A in the field of fractions K, and by definition it is integral over A if A satisfies such an equation. So this is a monic equation where the coefficients are all taken from the ring A. So this is the definition of x being integral over A. So we have to plug in A for x. So this A is, if you plug in A here, it will satisfy this equation. So A satisfies this equation. So now we can write A as R over S because A is in some field of fractions, and obviously S is not equal to 0, where R and S are in A because this K is nothing but field of fractions. So elements of K look like P over Q, where P is in ring A and Q is in ring A, and we choose them in the form that they do not have any common factors. So greatest common divisor of R and S is 1. So now we plug A in this equation. So instead of A, we plug in R by S in this equation, and then you multiply throughout by Sn. So the first here you will get R by Sn, then you have An minus 1. Instead of x we are plugging in A, which is R by S, so you have R by S n minus 1, and so on. So instead of x here we have R by S. Now you multiply this entire equation throughout, both left hand side and right hand side, by s to the n. So you multiply by s to the n. The first thing you get is Rn here, then An minus 1, Rn minus 1 S, because you have s to the power of n minus 1 in the denominator. Here you just have times s to the power of n. So you get an equation like this. So we want to show that this s is actually a unit in A itself. So A would be equal to R times the inverse of S, which will lie in A because S is a unit. So you can actually invert it in A itself. So if this is so, then we are done. So this is what we want to show, because you start with A in field of fractions, it satisfies such an equation, and we want to show that therefore A would lie in A, and this will suffice. So the only thing now left to show is that S is a unit. So we will proceed by contradiction. Suppose S is not a unit, then there is some prime P which would divide S. So this would imply that P divides Rn, because this Rn you can write it as equal to this entire side you can take on right hand side. So this right hand side would be divisible by P, therefore P has to divide Rn because each of the factors has S in it, and P divides S. So P divides this, P divides next factor, P divides this, P divides this. So P has to divide Rn. Now since P is prime, if it divides Rn, then it will divide R. So P divides S implies that P divides R, and this contradicts that greatest common divisor of R and S is 1, because now we are having P which divides both S and R. So it must be the case that our supposition was incorrect. So we have a contradiction, and therefore uh, S is a unit. So we cannot suppose that S is not a unit. Now let us see some examples which stem out from this theorem. Now this integers is a unique factorization domain. So this integers is sitting inside its field of fractions, which is rationals. So this Z is integrally closed. Now you can write Z plus Zi. This I here is nothing but square root of minus 1. So this I in red is square root of minus 1. So field of fraction of this is you join this square root of minus 1 or complex I to Q. So this is integrally closed because this is a unique factorization domain, or factorial for short. Again, Z plus Z root 2, this lies in this rationals root 2. So this is field of fractions for this, and this is integrally closed because this is a UFT. So again, this is a UFT. Its field of fractions is root 6 adjoined to rationals. So this is also integrally closed. Now we give an example of something which is not integrally closed. So consider this equation, x square minus x plus 1. So this equation is zx because all the coefficients are in z. So the root of this equation is 1 plus square root of minus 3 divided by 2. So alpha is integral over integers because this is a monic polynomial. All the coefficients are in integers. The coefficient here is 1, so it is monic. So alpha is integral over integers, so obviously it is integral over this bigger thing, because again the coefficients here are also contained within this ring, z plus z minus 3. But notice that alpha does not lie in z plus z minus 3 because you're dividing by 2 here. So you have a fraction 1 by 2, and that does not lie in integers. But alpha does lie in this bigger field of fractions. Rationals are joined with minus 3. So alpha lies in the ring of fractions of z plus z minus 3, but alpha does not lie in here. So this is not integrally closed because we have something which lies in the ring of fractions. It satisfies the equation like this, but it does not lie in here. So it is not integrally closed. So now we take another example from algebraic geometry. So say ring is this A, you join t square and t cube to k, and this sits normally inside this ring B, which is just t adjoined to k. So field of fractions for A and field of fractions for B is this kt. So so this is the field of fractions for B as well as A. So integral closure of A is actually B. So if you find out integral closure of A, it is B, which is a unique factorization domain. Now A is not integrally closed because there is a singularity at the origin for this curve y square equals to x cube, and this is the curve which corresponds to this ring A, and because of singularity here, this is not integrally closed. Now we come to an important remark, again used in algebraic geometry. So a scheme X is normal if all its stalks, so if all its stalks at every point which is OXX are normal for you taking any point X in this X. So X is this space which is a scheme. Take a point, on this point sits our stalk which is this, and this stalk is normal, then the scheme is called normal. So schemes, this affine scheme and projective affine space and projective space, they are normal because their local rings are factorial. So factorial is another name for unique factorization domain. So recall what is an algebraic integer. So a complex number that is integral over integers is called a algebraic integer, and algebraic number is again a complex number that is integral over rationals is called a algebraic number. So now the theorem. Every algebraic number is of the form a over b, where a is an algebraic integer and b is just a ordinary non-zero integer. So that is b just lies in integers, and from here you just take 0 out. So we will show this. So let's start C be an algebraic number. So this is the definition of algebraic number. So it's a complex number which is integral over rationals. So we will have a monic polynomial, and you plug in c in that monic polynomial. So some polynomial xn a n minus 1 xn minus 1 plus a1x plus a0 equal to 0, where all these ai's are rational numbers because it is integral over rationals, and you c is an algebraic number, so you plug in c, this equation will be equal to 0. But since each of these ai's is a rational, you can write it in the form sum numerator over denominator. Numerator is an integer and denominator is a non-zero integer. So now we can talk about least common multiple of this di. So take b as the least common multiple of these denominators, and this is an integer, and this is a non-zero integer precisely because all these di's are also non-zero integers. So we will now show that b times c, so this b, which is least common multiple of denominators of all these a0 a1 an minus 1, so least common multiple of denominators of all these rational numbers, times this c, an algebraic number, this bc is an algebraic integer. So this we have to show. So if bc is an algebraic integer, say a, then this would imply that c is equal to a over b, where b we just said is a non-zero ordinary integer. So b is an ordinary integer, and this a, we will show that a is a algebraic integer. So we will be done with the proof. We would have shown that b is a non-zero integer, which is just the LCM of non-zero integers, and a we have to show as a algebraic integer, and that's the end of the story here. A is algebraic integer, b is non-zero integer. So to show bc is algebraic integer, we have to work here. So we have to construct a equation, a monic polynomial whose root is bc and its coefficients should be in integers. So here the coefficients were in rationals, here the coefficients are in integers. So again, this monic polynomial is something like this: xn plus some constant times this is xn minus 1, and so on. So first thing you notice is that b an minus 1 is an integer, because b is least common multiple. If you multiply b with an minus 1, the denominator would cancel out, so you will get an integer. So this is an integer. Similarly, every term here is an integer. So this is obviously an integer because b to the power of n is an integer. So all these are integer coefficients. So now we just need to show that there is some polynomial like this which exists, but we are just going to take the same polynomial which was here and we're going to multiply. So this equation is satisfied by c. Now you multiply both sides by b to the n, so you get bcn here, then you have bn minus 1 here and b here, and so on. So each of these terms, ban minus 1, and then here second term would be b square an minus 2. This would be an integer because this b will cancel out the denominators in an minus 2, and so on. So each of these coefficients is again an integer. So we have been able to find a polynomial which was just this polynomial here, and bc is an algebraic integer. So this shows that bc is a root of a monic polynomial with coefficients in integers, and therefore bc is an algebraic integer, which we wanted to show.